Good morning, organic chemistry. This video is going to hit one of my favorite topics ever, IR spectroscopy. All right, so this video, we're going to have to probably shoot in a series. I've got to keep them a little bit short so they save. So this is video number 1. So if you are just starting these, this is our first video, and we're going to take this first video to really define our IR spectroscopy. Now, we're not going to get super deep. We're just starting with OChem 1. You are going to see IR again in OChem 2. So we're going to keep it just a little bit applications-based, and you might get a little bit deeper when you see it again in OChem 2. But I like to start it in OChem 1 because I want to get our brains working in a way that's helpful in our later classes. And we're going to include IR spectroscopy with our roadmaps. So if you're wondering, how am I going to see these problems? They're going to be like roadmaps. We're going to take that general formula and we're going to write out possibilities, and then we're going to use IR spectroscopy to slim down what those possible structures are. So you know how I love my roadmaps. We're actually going to make them better. And we're going to see IR and roadmaps on every test for the rest of this semester. So it's really not going anywhere. So let's take this first video to actually define IR spectroscopy and look at what spectra will look like and what they tell us. And then we're going to break it apart and actually apply IR spectroscopy. Now, this Word document is huge. Don't let that be intimidating. I made it huge on purpose, and I'm posting it on Blackboard because most of it is resources. We need some tables and places to look up IR spectroscopy. So our actual section of IR spectroscopy for us isn't going to be huge, but I wanted you to have plenty of resources. So I'm taking a few things from Wikipedia. I actually just gave the link to Wikipedia because it's got cute visuals on bond movements. So that one is really good. You don't have to feel like you need to read the whole thing, but we're going to talk in a minute about the motions of bonds. And I love Wikipedia's site. It just has some of those motions to give you a visual. And then one of my favorite links for IR spectroscopy is our virtual text from MSU. They have a really good website for IR. So if you're looking for the first place you want to learn a little bit about IR, I would look at that website. And then, of course, we've gone to Zero textbook. So this is the link to this section in our Chemistry Libre texts. I would look at that maybe number 2 and maybe this one number 1. And then I'm finding that Mastering in Organic Chemistry has some pretty cute ways of really slimming this down and looking at it and some study aids. And in fact, we're going to use one of their visuals in this video. So if you want to check those out, that would be awesome. So especially my MCAT takers, I think you'll find some good study techniques on that Master Organic Chemistry for IR spectroscopy, and you definitely have spectroscopy on those tests. So it's a good place to start. I want to take us on a journey, shut the front door, all the way back to Gen Chem 1. I want to do a 5-minute review of some basics for chemistry, and then I want to work my way into IR spectroscopy. And I want to start with something you've probably not seen for a while, but maybe we can brush off the cobwebs and picture our little atom back in the day from Gen Chem 1 when we were looking at that Bohr atom. Okay, now this is, if you looked at the history of the atom in your Gen Chem 1, this would have been in the late teens to early 20s. Our version or our visual of an atom. Now, Niels Bohr and Rydberg actually had some pretty profound ideas about electrons at the time. And a lot of those are holding true today. So even though we changed what the atom actually looked like in the 1930s, these principles have stuck. They are set. And that is how electrons interact with light. Now let's give some credit to Max Planck. And that equation, his equation for the energy of light corresponding to frequency with those photons, or as he called it, his little energy packets. So within light, there are photons, those little energy packets, and Einstein used those to explain how light interacts with an actual electron, and then Bohr took that idea to explain what happens to an atom when you shoot light at an atom. So what he explained was, between all of these guys in the 19-teens to 1920s, was that electrons can actually absorb photons. And it's typically given this little abbreviation for organic chemistry. So if you ever see, that's why I gave you the Planck equation. So when you see this, you're just going to picture light. So our little electrons can actually absorb a photon of light. And what happens is that that electron takes on that energy. That energy is absorbed. Well, we correlate energy with where that electron is. So what you learned in Gen Chem 1 was that if an electron absorbs an light, it's got to move. It's got to change its energy state. So you drew a little drawing like this in your Gen Chem 1, where your little electrons were jumping orbitals. Okay, we know that that visual has changed in the last 100 years, but the process is still the same. We have just now gone to a different energy level. So we've gone maybe from n equals 1 to n equals 2. We've changed that energy level. And then the reverse process is also true. Bohr and Rydberg saw this in the difference between an emission spectrum and an absorbance spectrum. So electrons can also give those photons back. And we learned this in Gen Chem 1, that our light and our electrons interact with each other. And you probably forgot it. Oh, whatever, I did awesome on that test and I moved on. But it turns out that this philosophy is the basis for so much instrumentation that we still use today in chemistry. One of the oldest and the first was IR spectroscopy. So we're going to take this idea that electrons can absorb light, and they're going to absorb that energy. And literally, it's going to change the energy of that electron. All that process is staying. And then we're going to use it. So even though we looked at this in Gen Chem 1 for the atom, let's get deep for a second. Electrons are also in our molecules. They haven't gone anywhere. And electrons form bonds. So in Gen Chem 1, you looked at the atom. In OChem 1, we're going to take this entire concept and apply it to bonds. We had one last theory in here as we're getting into the 1930s. That is that this energy is specific. So the energy that is absorbed by that photon is very specific. In other words, if we look at our electromagnetic radiation spectrum, and we go all the way down here from radio waves all the way up to gamma, our little electrons don't absorb all of this range. They absorb specific sections. And we see this in atomic absorption and emission. They absorb specific wavelengths and frequencies. Now we're going to take this idea and use it. Okay, let's draw an atom. and let's get a little bit deeper. So let's draw methane. Let's start with our most basic atom. We drew our orbitals and we drew how bonding had to happen back in our first day together. So let's look at that again. If we're looking at a carbon and a hydrogen, we're going to picture just one bond between carbon and hydrogen. You've got an electron from carbon and an electron from hydrogen that have to meet and share space in a bond. So we drew our little orbitals. But I want to go back for a second. This electron was in the 2 energy level. This electron was in that 1 energy level. They have specific energies. And when they come together and bond, they're going to have their own energy. So that was our molecular orbitals that we created. That is that LUMO orbital. Oh, let me pause. I just goofed that up. That is our HOMO, our LUMO. I had a brain freeze there. Our LUMO is up here. All right, so that specific energy within that bond is coming from the fact that you had this carbon and this hydrogen, and it's giving you this energy in that orbital, and that's going to determine the specific wavelengths, frequencies, and energies that are absorbed. Okay, now this seems crazy at first, but hang on a second, watch this, and then it's gonna make sense why we give a crap. All right, so let's take our methane and let's just convert it to methanol. Okay, so now let's look at this bond would have that specific energy, but would this bond have the same energy? No, it's going to have its own specific energy. Why? Because now that energy is coming from a carbon and an oxygen. And so now when you bond, this energy is going to be totally different than our carbon-hydrogen energy. So then you see where I'm headed. What about the energy here? That is going to be its own energy as well, because now you're combining an oxygen and a hydrogen. Okay, what's different then between methane and methanol? Your functional group. You have got 3 sets of bonds that will absorb and emit energy in a different specific range of the EMR. Okay, that's super deep. I feel like that almost needs a sparkle pen. All right, so each bond type, okay, what does bond type equal? Our functional groups. What? Each functional group has a different bond type. That bond type will absorb and emit in different, very specific wavelengths, frequencies, and energies in the electromagnetic radiation spectrum. So let's put that into even more detail. Specifically to covalent bonds, that's what we're looking at. Our covalent bonds themselves in general tend to emit and absorb in the IR range. This is what heats our planet. This is phenomenally important, this little tidbit. This is why methane, carbon dioxide, water, all of them have covalent bonds. All of them are a big topic in the news on global warming because they are in the atmosphere and they are absorbing IR. IR is heat. So they're absorbing and emitting that heat from the sun, and they're emitting it back to the planet, and they're reabsorbing it, and that cycle is what makes our planet livable. So we're also going to take this idea and apply it to an instrument. So I need just a little bit more space. So let me give myself just another page here. I need just a little space. It turns out I wrote kind of big. So let's get my little, let's try and insert a page here. It won't let me until I bring up my, there it is. Let's insert a page. Okay, done. So now let's take and apply this idea. We have the idea that somehow in the IR range, we're going to hit covalent bonds. And we've got this idea that functional groups are going to absorb and emit a little bit different within that range. So how can we take this and use it to identify functional groups? Well, this is one of our oldest instruments in organic chemistry, and it is still widely used today. In fact, we have one in the lab, and we use it almost daily, and you will use it in the lab for this course. So this video will also be put under our clove oil experiment. So let's get practical. Let's say you take an organic sample, and it's a mystery. I wonder what it is. And we are going to shine light through it. We're going to get fancy, and we're going to have the world's fanciest light source or light bulb. It is going to be specific in the IR range, but we want to get even fancier than that. We don't want just willy-nilly IR. We want to tell specifically where in the IR range of our spectrum we're absorbing and emitting light. So this light source actually starts all the way down here at what's called a wave number, 4,000, and it typically goes to about 500. And this is correlating to our wavelength, and this is in the IR range of light, of our electromagnetic radiation. And then we want to pass it through the sample. Okay, but wait a second. What do you do with a liquid sample? Well, we're going to take and put a drop on a salt plate, and that is literally salt. It is salt that is pressurized, or KBR, we do both in our lab. That is literally salt that has been pressurized and solidified into a nice see-through plate. Now, why salt? Oh, what kind of bond is in salt? That is ionic. So it turns out that those bonds are basically invisible in the IR range. So it's a place to hold our sample that won't interfere with our absorbance and emission. So our world's fanciest flashlight here is going to start on this end of that range and work its way through this end of the range as a flow. So it's starting here at 4,000 wave numbers, and it's then slowly working its way all the way down to 500 in those wave numbers. And then, but wait a second, how are we going to know anything? So with every IR spectroscopy, you need your fancy light source, and then you're going to literally wait and see what is absorbed and what is emitted coming out the other side of your sample. So you need to have something over here that is going to detect our IR that is coming through. So if our sample has a functional group that absorbs at, let's say, 300 wave number, well, now in your detector, if your light is passing through, now you're missing that 3,000 wave number in your detector. So we're going to start down on one end of the range, and detectors, there are many. There are lots of ways to detect that light, so we won't get too deep in that, but a basic IR is your light source that has to be on a gradient. And then you have to have a detector that can detect that light that's coming back out. So how does an actual IR spectrum look? Well, you'll always notice them. They will be down here somewhere around 4,000 to 500. Their units will be that wave number. And what you're going to look at is starting right here, up here in 100% is called transmission or transmittance. How much light is coming through? Okay, so my sample way over here did not hit a functional group it absorbs yet. Oh, hang on a second. We've just absorbed here. So your sample just absorbed light in that 3,300 range. And then as we keep going, maybe you've absorbed some right here. Maybe we've got one right there. Maybe we've got some little baby ones here. And then maybe we've got a huge one here. And then as we get close to 1,000, it starts to get a little crazy. So now we're going to get a lot. This is called the fingerprint region. So now let's add in theory for a second. Shut the front door. If our absorbances are very specific to functional group, all we need then, shut up, this is so fun. What do we need? We would need to correlate where we absorb to that type of bond. So because IR has been around for a couple hundred years, we can say, look, around 3,300, well, shut the front door, that is an NH bond. That is very specific to that type of bond. Aha, around 3,000, that is very specific to a CH bond. Around 2,000 is very specific to a triple bond. Around 1760 is specific to a carbon double bond oxygen bond. Each one of these absorbances can connect to functional group. They are specific to a type of bond, and then it's up to us to connect that to a functional group. So IR is extremely powerful. It can tell you functional groups that you have, and it can tell you functional groups that you don't have. So this is all about detecting functional groups. The one thing it doesn't is tell you how many functional groups you have. It just tells you what's present. So that's another instrument that will tell us how many. And when we get into OChem 2, we'll use NMR for that. So we are going to use IR specifically to identify functional groups. And we're going to use it to identify what we have and what we do not have. So let's pause this video and then let's show you how to read an IR spectra. And then you guessed it, the rest of this document is actually tables that are going to connect where our bonds absorb and how you can connect that to functional group. So this is just our beginning video. Let's pause this one.